Today, as a part of this session, SAS407 will walk you through how you could build various multi-tenant GenAI architectures. Primarily, we'll walk you through how you could resolve various SaaS architecture challenges so that it will yield you a robust GenAI multi-tenant architecture. This is a 400 level session. We'll go deeper into the code. Primarily, when we are talking about resolving various SaaS architecture challenges, we'll bring up a piece of a code and try to walk you through about how you could resolve a particular challenge and explain how that would yield you a robust GenAI architectures. And at the end of this session, we'll provide you some GitHub repo links, which will have most of those codes, and also provide you a repo link of a workshop which we built, a new workshop which we built, which kind of like covers most of the concepts which we are going to talk about today. Having said that, myself, Ujjwal Bukka, I am a senior solution architect from AWS SaaS Factory team. My team primarily helps various ISVs and enterprises with their SaaS journey. We provide business and technical guidance through which we try to accelerate their SaaS journey. Along with me is my colleague.
Hi, everyone. My name is Mehran Najafi. I'm a principal solution architect based in Toronto, Canada. Very happy to be here, the first day of re:Invent, and talking about GenAI and multi-tenancy. So as you all know, building a solution that has a built-in LLM could be complex to even serve one customer. We are dealing with LLM. Either you need to host it on your hardware accelerators, which could be expensive, or you are using some SaaS solution pay per token that also could be complex and expensive. You may need to fine-tune your model to serve your customer. Then you need to host it. You are dealing with the customer data. The customer data could be sensitive, confidential. And if you are using some agentic workflow, then you are dealing with a complex agent as well. So that agent needs to have access to the API and to other databases or third party. So even serving a single customer could be complex. Now let's think of just scaling it to thousands of tenants, thousands of customers. So we have even more challenges and more problems. That we are dealing with multiple LLM that might have been fine-tuned to serve each domain or each type of your users. Now we are dealing with lots of customer data. We need to make sure that one customer doesn't have accidentally or purposely access to another customer data. The cost for some of the use cases could be just exponentially higher. That makes some use cases just economically not feasible. Or agents. Now we are dealing with many, many agents, right? So there are many architecture challenges that in this talk with Ujjwal, we are going to look at many of them and see that how AWS with the managed solution can help you to scale your multi-tenant LLM-based solution, that you really can focus on the area that are more specific to your solution, and you leave those complex parts to AWS. So first, let's look at two popular GenAI architectures. When you want to build LLM-based solution, as you may know, very popular use case or very popular architecture is building it through the RAG. The other one that we are going to talk is through the fine-tuning. But in a RAG, the idea here is that we leverage a generic LLM. We don't go through customization and fine-tuning. We use an LLM that has already been trained based on lots of data. We use it as it is. How we can make it more specific to our customer requests is through the RAG. RAG stands for Retrieval Augmented Generation. Here we have customer data that we embed. We use some vector databases. We embed them, vectorize them. That knowledge will be stored inside that vector store. Then when that user request comes, the user request go to the vector store. We use some similarity search functionality of that database to retrieve those knowledge relevant to that user prompt or user query. Then we provide that to our LLM. I'm pretty sure everyone heard about Amazon Bedrock. Amazon Bedrock is like AWS way of connecting you to lots of different LLM options. Bedrock send that request with those relevant knowledge to the LLM behind Bedrock. That could be from Amazon, like Amazon Titan, from our partner, Anthropic, Claude, Meta, Llama 3, Cohere, or others. And then the response will be generated and back to the user. So that's our RAG. Then the other pattern is using fine-tuning. Here, the purpose is we don't send those contexts or those relevant knowledge every time. That could add to the length of your prompt. Instead of doing this, we use that training data from our user to fine-tune a model. So go through the training job, fine-tuning it, customizing that LLM to have those knowledge already embedded into our model. So when we have that fine-tuned model, when a user request comes, then that already know about that background, that knowledge. So a response will be generated and sent to that user. A couple of points here. First, so in many use cases, we may use RAG or we may use fine-tuning. Each has its own pros and cons. For RAG, it's much simpler on the LLM because we don't have to fine-tune. And also, we can use those generic shared one. On the fine-tuning, no, we need to go through the fine-tuning. Then when we have an LLM, that's a customized and that's fine-tuned for our own use case. That means that we need to host it. We need to pay for those accelerator, those hardware behind the scene. However, we are saving on the length of our prompt. We don't have to include those contexts every time that the user prompt will be sent to the LLM. But as we will see, in some cases, we are using the combination of these two. We have a RAG architecture, which instead of using that generic LLM, we are using a fine-tuned model. Just for, you can think of, we use the static data to fine-tune a model. And for that dynamic piece that we don't want to fine-tune a model every minute or every night or every week, so we use that portion as a RAG. So we will see it shortly. The second point, as I mentioned, and the purpose of this session is that help you to see how AWS with managed services can help you abstract away lots of this complexity for you, that you can build a multi-tenant solution easier. In terms of RAG, Amazon Bedrock has a feature called Amazon Bedrock Knowledge Base that is basically like a managed RAG. It helps you to connect your Bedrock knowledge base to a data store, that like S3, that you have your user data there. Then you connect it to a vector store. Could be OpenSearch serverless for this talk, or it could be other option. And you can configure LLM, which LLM to use. Then Amazon Bedrock knowledge base, it does everything for you. It embeds the data, put them into a vector store. It does the retrieval, and it sends it to the Bedrock. Whatever I put it here, it can be just abstracted away into the Amazon Bedrock knowledge base. On the other hand, for fine-tuning, Amazon Bedrock has a customized model feature that you just need to point Bedrock to where your data is stored, and then you define which LLM you want to customize. Then it runs the customization job for you. So really, you will get these out of the box, and you can focus on how we can now put them into the multi-tenancy. Now, let's look at just a scale, what I said for one user, and see where are those multi-tenancy aspects come into picture. Now we don't have only one user. We have a number of tenants. You see here 2, but it could be thousands. Let's say with 2 tenants, each tenant has its own data store. We need to store them into a vector store. Very first challenge here is that how many vector store? Do we want to use one vector store for vectorizing our tenant? Or we want to have an isolated one and we have multiple of them? In any way, we need to make sure that each tenant knowledge is isolated, that is not mixed with the other tenant knowledge. Next, we need to put them into a SaaS solution framework. So SaaS is not just about serving one customer. We have a number of tasks for onboarding a tenant, for provisioning resources for that tenant, because each tenant may have some specific dedicated resources, and also tenant management, for billing, monitoring, control, whatever. So here we need to also look at the SaaS solution that support LLM. And then when a user sends a prompt through that SaaS solution, that go to our vector store that has multi-tenant knowledge embedded there. And with the tenant context, that relevant knowledge will be extracted, and then that will be sent to the bedrock, the LLM basically behind the bedrock. This is RAG. We don't need to fine-tune a model. We don't need to customize a model. So we can use the same generic shared LLM to serve our tenant. So this was on the RAG, when we have multi-tenancy there. For fine-tuning, now we have not one user. We have a number of tenants. Each tenant has its own data store. We use Bedrock customization feature to create a fine-tuned model for each of those tenants. Using Bedrock, we can host each of those on a provisioned throughput model that enables us that the other tenant or the other user will not have access to that tenant. So those LLM are dedicated to each of our tenants. Now, when the tenant request comes through that SaaS solution, it will be sent to the fine-tuned model associated with that specific tenant. So this is a very high level of how this RAG and fine-tuning would look like in a context of multi-tenancy. Now we want to go deeper into each of the SaaS and multi-tenancy challenges and see that how we can address those. When we look at the SaaS, you may familiar, there are a number of isolation pattern. One of them is called pool, that we are utilizing the shared resources. So we try to use the same service, but use them for multiple tenants. On the other extreme, we have silo, that we dedicate resources to each tenant. So in this talk, we are going to look at these two extremes, but for your own use case, your own application, you can look at something in the middle, based on what makes sense to have a shared services and what it makes sense to have a dedicated services. Very first question that probably every SaaS provider will answer is that how you want your user experience to be. For GenAI, more specifically, it's new, right? So many customers, they want to try your service before getting into a more expensive and more paid experience. It's good to have a tiering strategy to support different type of users. What's important here is that for your basic tier, we have the most economically feasible architecture because you don't want to make it expensive, then you are losing money. So you really want to keep it as less expensive as possible. Then we are using more like a pool, the shared services. We want to use as many shared services as possible, but at the same time, we need to have those tenant isolation, those scaling, all of those aspects as well. So for basic tier, as I mentioned, the goal here is to use as many shared services as possible. And we are using RAG here. Why we are using RAG? Because we want to use the LLM probably is the most complex and expensive part of solution. We don't want to go through the fine-tuning because when you fine-tune for one tenant, the other tenant cannot use them. Then you need to host them. You need to pay per hour. You cannot pay per token in most of the cases. When we look at the premium tier, we are looking at more like a RAG plus fine-tuning. But here, for basic tier, we are using RAG. First, we have a storage. We need to store our tenant data. We are utilizing even one. Remember, this is an extreme case. So we are using one bucket, but inside that bucket, we dedicate prefixes to each of our tenants. Then we are using Amazon Bedrock knowledge base. Amazon Bedrock knowledge base is an abstraction layer. It means that by itself, it doesn't have any cost. The cost coming from the resources and the services that it uses. In knowledge base, we connected to a storage. This is our S3. Then the data is injected, and the knowledge base use Bedrock to embed and vectorize those data and store them into our vector store. For vector store, we are using Amazon OpenSearch Serverless, which enable us to use the same collection, but using tenant-specific indexes inside that collection. So we can have many indexes. Each index represents one tenant in our collection. We don't have to have a different collection for different tenants. Now, when a tenant and other tenant, each of these basic tier tenant request comes, go through the API gateway, that again is going to be shared. Then we have some pool compute. This could be a Lambda function, this could be EC2, like EC2, EKS, ECS, whatever. It has the logic of calling the LLM. This is RAG. Very first step is to retrieving the knowledge relevant to that prompt. That go to the tenant one knowledge base. The knowledge base go through the OpenSearch serverless and find those relevant knowledge. And then that request will be sent to that shared Bedrock. So, and we are paying basically per token. If this is the agentic workflow, it means that it's not about question answering. We need some task to be done. We want some API to be called, some data to be retrieved from a database. We are using a shared agent. So Bedrock agent can also support multi-tenancy. With some context, it decides which API gateway, which API and which action group to call or which database it goes. Here, because we only have one agent and we have multiple knowledge bases, each knowledge base per tenant, as we will see later in Premium. So in Premium, we will have a one-to-one relation between agent and knowledge base, but here agent need to look at the context, decide about which tenant ID, and then go to that specific knowledge base for that tenant. Very similar, for tenant 2, we have a dedicated prefix into our S3 that go to its own knowledge base. We have a dedicated index inside the OpenSearch serverless. And then when a tenant 2 request comes, it go all the way to the Bedrock and to the tenant 2 knowledge base to serve that tenant. Now, let's look at the premium tier. Premium tier is the tier that they are already paying. So we want to provide the best user experience, the lowest latency, the most isolation for them. And we are looking at the silo pattern, dedicated services, for each of those services that we have in our pattern. We are using RAG plus fine-tuning. First, we use data or training data to fine-tune a model using Amazon Bedrock customized model. We have a fine-tuned model for this tenant. Now for the RAG portion of the solution, again, we have a data, put them into the knowledge base. This is probably more the data with the dynamic nature. We have a dedicated OpenSearch serverless collection for each tenant, and we have an index inside that. So when a request comes, we have a dedicated even API gateway. We have a dedicated compute, like a dedicated Lambda, dedicated EC2. I know we have a workshop on this, and we have some working code in a Git repo so you can use. It goes to its dedicated knowledge base, the request to retrieve the data from the open. Go from the shared to the dedicated resources to support both of these and premium. And if it is agentic workflow, we have a dedicated agent for this premium tier that go to its dedicated action group with API and databases or any other third party that this agent to perform the job. So the next challenge is we want to build a SaaS solution. As you for component, one is the control plane, the SaaS control plane, that it solves the issue on the tenant onboarding. You want your tenant information, the payment data, the type of tier that they want to join, basic or premium. And also looking at the tenant management. You want to collect some metric, how the user are using your service, looking at the log, using all those data that help you to basically monitor those tenant activity inside your solution. For the tenant provisioning, there are some resources that need to be provisioned when that tenant is onboarded. And this is different for basic and premium tier. For basic, we are using mostly the shared services. It means that even before any tenant onboarded into the system, those services exist. Here we have a pool S3 dedicated bucket, which is empty. We have a pool OpenSearch serverless collection. Again, no index is there. We have an agent that already set up. Then when a new basic tier tenant is onboarded, what we need to do is to create a prefix for that tenant. We need to create an index inside our OpenSearch, and then we create a knowledge base. This could be quicker because most of those services already exist there. On the other hand, for a premium tier, we start with empty, right? There is nothing there. When a premium tenant is onboarded, then we create a dedicated S3, dedicated fine-tune model. We have a dedicated knowledge base, and also a dedicated OpenSearch serverless collection. The next challenge to look at is data partitioning. So data partitioning is very important in SaaS because it's very important. We are dealing with lots of tenant data, lots of customer data. We want to enforce the isolation as much as possible. So no one tenant should access to the other tenant. In order to later, we will look at how we enforce the isolation. Really, the first step is that we logically and physically partition data in a way that isolation can apply there efficiently. Our basic tier, we are using shared services. The isolation is inside those shared services. For S3, we have a dedicated prefix to each of our tenants. For OpenSearch serverless, for vector store is dedicated index. And the good news here is that the knowledge base is abstracted, so we really don't have to put that into a pool, so it's already assigned to our tenant. So every tenant has its own dedicated knowledge base. For premium, it's much simpler because we have a dedicated resources, dedicated bucket, dedicated OpenSearch serverless cluster, and the same. The knowledge base is dedicated to this type of tenant. So next, my colleague is going to talk about the isolation.
Thanks, Mehran. So the next architecture challenge which we'll talk about is tenant isolation. Tenant isolation means you need to make sure a particular tenant is able to access only tenant-specific resources. What we'll do here is first we'll pick the basic tier and the premium tier. We'll try to highlight the areas of the architecture where we need to implement tenant isolation, and then we'll deep dive into and talk about how you could implement tenant isolation. So start off with basic tier. You have seen this basic tier architecture. The areas where in this architecture you need to implement tenant isolation is knowledge base. So we are creating a knowledge base for each of your tenant, and then we need to make sure this knowledge base is only pulling the data from the tenant-specific prefix and pushing and pulling the data from the tenant-specific index in the shared pool collection. Next, the pool compute. This pool compute is shared across multiple tenants, so the services in this compute are shared across multiple tenants, so you could not directly attach an execution role to it, which gives you a broader scope which would access all the tenant resources. Instead, what you need to do is basically enrich these services in such a way that they generate the scoped credentials in runtime which are specific to this particular tenant and use those scope credentials to access tenant-specific resources. In a bit second here, we'll talk about how to implement that. And the pool agent. The pool agent, again, the same story. It interacts with tenants, resources, so it is shared across multiple tenants. So we need to make sure this pool agent is enriched in such a way that it uses the scope credentials which are generated in runtime, which are specific to that particular tenant, and then uses that scope credentials to interact with tenant-specific resources. And again, in a bit second, we'll understand how to implement tenant isolation for this. The other angle to here is, the other part here is we need to make sure that this knowledge base is only able to push and pull the data from the tenant-specific index. And the way you do that is by leveraging a data access policy which is defined at the OpenSearch serverless collection. Think about this as more as a OpenSearch serverless collection. If you look at that policy, what you will see is a principal. That principal is basically nothing but the service role of the knowledge base. And if you look at the permissions of that, you could see that this knowledge base is only empowered to push and pull the data from the tenant-specific index. This is how you make sure the tenant-specific index. And this is how you would enforce tenant isolation for the knowledge base. Moving on, for the pooled compute, as I mentioned earlier, we need to make sure this pooled compute in real time generates the scope credentials which are specific to this particular tenant and use those scope credentials to interact with tenant-specific resources. Now let's understand how we could implement that. I'll try to give you an example. Interacting with the API gateway, at the token, placing a placeholder. This is how you define in a back role. So now what the Lambda authorizer does is, from the JWT token, it gets the tenant ID, it reaches out to the control plane to get the knowledge base ID of that particular tenant. When you're onboarding a tenant, when you could, not sure whether you observed, there is a service called tenant management service, which kind of like captures the tenant-specific metadata or the metadata which is generated during the onboarding. So it has captured the knowledge base ID of that particular tenant when you're onboarding a tenant. In this case, tenant 1. So now, coming back to the Lambda authorizer from the JWT token gets the tenant ID, goes to the control plane, gets the knowledge base ID, and then takes the knowledge base ID and this ABAC role and interacts with a service called security token service. Basically, it makes an API call and sends these two things as a parameters and get back the scope or credentials which are specific to that particular tenant, which give access only to the tenant-specific resources. And those credentials will be passed on to the backend service, and the service would use those scope credentials to interact with the tenant-specific resources. Now, let's double-click on the Lambda authorizer code, and also we'll look at the service code to understand this in a bit more detail. So if you look at the Lambda authorizer code, the first thing the Lambda authorizer does is it validates the JWT token. From the JWT token, it gets the tenant ID, and then taking the tenant ID, it makes an API call to the control plane to get the knowledge base ID from the control plane. And once it gets that information, it makes a call to a assume role method. If you look at the definition of that particular method, within that assume role method definition, the first thing what you are doing is basically you are making an API call or to the security token service where you are passing the role which you want to assume and also the additional parameters which you want to replace in that role, in this case the knowledge base ID. Once you do that, the response of that method invocation, what you get back is the scope credentials. From that response, you could parse the scope credentials which are specific to this particular tenant, which give access only to this tenant-specific resources. And now, coming back to the Lambda authorizer, there you have to package a response, successful response or a failure response, so that the API gateway can authorize this request. As a part of that, as a part of that response, you could add these scope credentials and pass that response back to the API gateway, and the API gateway, in this case, would authorize the request and passes the response to the backend service. And if you move on to the backend service, if you look at the backend service code, the first thing the backend service code is doing is basically from the input event or the input request, it's kind of like getting the scope credentials which are specific to that particular tenant. Using that scope credentials, we are creating a Bodo3 client, in this case, the Bedrock client. This Bedrock client will give access only to the tenant-specific resources, that is the knowledge base in this case. And then, using this Bedrock client, you create a construct called knowledge base retriever. Basically, it's just a construct through which you could interact with the knowledge base. And you could see that when you're creating this construct, we are using the Bedrock Bodo3 client, which we created in the previous step using the scope credentials which are specific to this particular tenant. And then we put all these things together where you invoke the LLM by passing the input prompt and the knowledge base retriever. So the couple things happen here. So the input prompt will be sent to the knowledge base retriever to get the tenant-specific data, and then the input prompt and the tenant-specific data are put together and interacted with the LLM through Bedrock to get the final tenant-specific response. Now, moving on to the pooled agent. Again, here we'll use a similar approach, what we just talked about, and implement isolation. Let me give an example of that. Let's assume again tenant 1 is sending a request to the API gateway, and at the API gateway you have seen the same Lambda authorizer, and the Lambda authorizer validates the JWT token and then gets hold of this IAM role, which is similar to what we have seen it. And the Lambda authorizer, again, from the JWT token, gets the tenant ID, goes to the control plane, gets the knowledge base ID, and then passes the knowledge base ID and the role to the security token service and gets the scope credentials. And those scope credentials will pass to the backend service, and this backend service now, when it is invoking the agent, it will pass the scope credentials to the agent so that this agent will use the scope credentials, which are specific to that particular tenant, to interact with the tenant-specific resources, in this case, the knowledge base. And again, I'm just showing an example of knowledge base as a tenant-specific resource here, but you could apply this concept to any other tenant-specific resources like DynamoDB table or S3 bucket. Basically, you would enrich this IAM role with access to that S3 bucket or DynamoDB table. Now, let's double-click on this service code and the agent code and understand how all this comes together. So if you look at the service code, the first thing service code does is basically it gets the tenant-specific scope credentials. Once it gets the tenant-specific scope credentials, it invokes a call to invoke the agent. Invoking the agent, it passes the scope credentials through a session attribute. You could see that you are passing the scope credentials and also any additional metadata you want to pass, you can pass through the session attributes. At this point, the agent gets kicked in and agent code gets kicked in. And if you look at the first part, what code does is basically from the session attributes, you are parsing the scope credentials, or you are getting the scope credentials which are specific to this particular tenant. And also you could see there that it is also getting any additional metadata it requires. And once it gets the scope credentials, a similar story, we are creating a Bedrock client using the scope credentials, which will give access only to the tenant-specific resources. And now the agent code will try to invoke the other methods using that Bedrock client, which will give only to the tenant access to the tenant-specific resources. This is how isolation for a pool agent. Moving on to the premium tier, again, you have seen this premium tier architecture. The areas where you need to enforce tenant isolation would be the knowledge base and also the pool siloed compute. In here, since we are creating a dedicated compute for this particular tenant, the isolation story is pretty straightforward in the sense, since it's a dedicated compute, you could attach an execution role directly to this compute, which give access only to the tenant-specific resources. Similarly, we have a dedicated agent, which is specific to this particular tenant. You could pretty much attach an execution role to it, and then it will give you access to the tenant-specific resources. Now let's double-click on these three components and understand how you could enforce tenant isolation. Again, for the knowledge base, you've seen in the premium tier, we are creating a dedicated collection in the OpenShift serverless collection. And if you look at the knowledge base, for the knowledge base, you would attach a service role, and for the service role, to access the collection, and then interact with the embedding model. Here, you're making sure this knowledge base is only interacting with the dedicated S3 bucket. Since it's a dedicated S3 bucket, you're kind of like giving direct access to it. And then again, at the OpenShift serverless collection, you would use the data access policy. And if you look at the data access policy, the first thing you would see is you define the principal. And then if you look at the set of permissions where you are making sure this knowledge base is only interacting with this dedicated collection in this case. This is how you would enforce tenant isolation in the case of premium tier for the knowledge base. For the siloed compute, let's take an example. Tenant 3 is interacting with your API gateway. The request goes to this dedicated compute, which has a dedicated service. Since it's a dedicated service, you could pretty much attach an execution role. And if you look at the execution role is basically giving permissions which are specific to this particular tenant. In this case, you are giving access to the tenant 3. Using these permissions, this service would interact with the knowledge base. And if you look at the service code, you would see that since it is a dedicated service, you could pretty much directly inject the knowledge base ID into it through the environmental variables or the environment variables. And then you would create the Bodo3 client, which is the Bedrock client. Since the service is directly attached to the execution, when you create this Bedrock client, it would get the permissions from that execution role. And then you would create the knowledge base retriever with this Bedrock client, which you created in the previous step. And then you would put all this together and then invoke the LLM by passing the input prompt and the knowledge base retriever. And for the silo agent, again, let's assume tenant 3 is interacting with the API gateway. The request goes to the service, and the service would invoke the agent. In this case, again, the agent, you would directly attach an agent execution role to the agent, which gives permissions to the tenant-specific resources. And that's how the agent would interact with the tenant-specific resources. And if you look at the code of this agent code, it's pretty straightforward. Basically, the service code is basically invoking the agent. And if you look at the agent code, it is getting all the permissions from the attached execution role. So it is just executes its methods, and using the permissions it's getting from the attached execution role. challenge which we'll talk about is how do we calculate cost per tenant for these architectures. In order to calculate cost per tenant, first we need to understand a couple things. When you are thinking of calculating cost per tenant, you need to capture metrics with the tenant context, specifically for the areas of your architecture where you want to measure the tenant resource consumption. So you basically capture the metrics, and then you need to aggregate the metrics. When you're aggregating the metrics, you aggregate those metrics by a tenant and get the percentage of consumption by each of your tenants. Once you get the percentage of consumption, you multiply that with the total cost of the service to get the cost per tenant. So basically, you need to capture the metrics with tenant context and aggregate the metrics. So when you're capturing the metrics, you need to, what we usually suggest is look at your architecture and try to pick the areas of your architecture which contributes most to your AWS bill. In this case, the most of your cost would be attributed from interactions with the large language model. So if you look at the basic tier and premium tier, you could see some various components of your architecture which kind of like interacts with the LLM. And you might be already familiar that the way the LLM charges you is based on the number of tokens, input tokens and output tokens generated when you are interacting with the large language model. So what I'm trying to get to here is, basically, we need to capture the number of input tokens and output tokens generated when various components of your architecture are interacting with the large language model. Here, I'll try to, across the basic tier and premium tier, I'll try to summarize the various components which interacts with the large language model. Those are, one, the compute. The compute interacts with the large language model primarily to get the final tenant-specific response. And in a bit second, we'll understand how you could capture the metrics with respect to the compute when it is interacting with the large language model. And then the knowledge base. The knowledge base again interacts with the large language model to primarily generate the embeddings. And then in a bit second, we will understand how to capture those metrics. And then the agent. As you've seen, we could assign a task to the agent. Agent interacts with the large language model and then performs its task. And then in a bit second, we'll understand how to capture those metrics. The idea is like once you capture those metrics, we get some kind of an hypothetical, a percentage of consumption here. Just I'm throwing you numbers here. But once you have this percentage of consumption across your tenants, you would multiply that against the service cost, in this case the bedrock, to get the cost per tenant for using the bedrock. The other area where we'll talk about capturing the metrics is the storage. Specifically for the basic tier, since the basic tier, you have seen that we are using a collection which is shared across multiple tenants, create index for each of your tenant. I'll walk you through how you could capture the metrics when you're using the shared pool collection, and then from that, how you could get the percentage of consumption. Once you remove these components from your architecture, the basic tier and premium tier, the only left out components, primarily in the premium tier, are these dedicated resources. These are dedicated resources which are specific to this particular tenant. In this case, since they are dedicated resources, you could use a different approach to calculate cost per tenant. That is basically you could tag them with tenant ID. And then using a cost and usage report, which will be, cost and usage report, which will be available from AWS billing and cost management service. You could pretty much aggregate your cost of these components, these dedicated components, by tenant ID, basically by the tag and tenant ID. So now let's pick up each of these components and drill down into it and understand how you could calculate, how you could capture the metrics with respect to when they are interacting with the large language model. To start off with, the compute. Let's assume multiple tenants are interacting with the API gateway. The request goes to the backend service, and this service would use some kind of an API to interact with the bedrock, and it gets back the response. So when you're interacting with this API, the API you could use is, if you are using a Converse API, the interactions between the service and the API, when the response which comes back from that Converse API will have the number of input tokens and output tokens generated for that particular interaction. So now what you could do is this service can use some kind of a library. In this case, I'm just showcasing a metrics manager library. Think of this as a piece of code which basically takes the tenant context and the output response, and then from the tenant context, it will get the tenant ID, and then from the response, it gets the number of input tokens and output tokens, and then tries to put them together and publishes to the CloudWatch logs. If you look at the code of this service, the way it would look like is, the first thing the service is basically doing is getting the scope credentials and create a Bedrock client, and then it creates a knowledge base retriever with that Bedrock client, and then you're invoking the LLM. This is where you would use the Converse API to invoke with the LLM, and once you do that, based upon the response, then you would use this metrics manager library where you could see that I'm passing the input event as a parameter. From there, it will get the input tenant context, that is the tenant ID, and then I'm also passing the number of input tokens and output tokens generated, which comes out of that particular response which you made, or the call which you made in the previous step, and then it would record the things in the CloudWatch log as shown here, where it captures the tenant ID along with the number of input tokens and output tokens generated for that particular interaction. And moving on to the knowledge base. For the knowledge base, first, before we understand how to capture the metrics, we need to understand what are the different areas where the knowledge base interacts with the large language model. First, when you're ingesting the data into the knowledge base, it interacts with the Bedrock to generate the embeddings. And the other use case where it will interact with the knowledge base interacts with the large language models is basically when a particular tenant request comes through, if the compute interacts with the knowledge base to get the tenant specific data, that's when the knowledge base interacts with the large language model through Bedrock. The challenge here is that the interactions between the knowledge base and the Bedrock comes out of the box for you. There is no way for you to inject some custom code to capture the metrics. One way to solve this challenge is at the Bedrock level, you could enable the logging. Once you enable the logging, the Bedrock would publish knowledge base and the logged message will look something like this, and within that log message, you could see that, as I highlighted, you could get the number of input tokens consumed for that particular interaction. Since the knowledge base deals with the embedding models, it only, deals with input tokens. There are no output tokens. This is good that, you got the number of input tokens, but the challenge is like, how do I attach the tenant context? So now one way to resolve this is adapt some kind of a convention where when you are defining your knowledge base, have that service role defined with the tenant ID. So if you look at this message, there is another attribute as I highlighted here. There is that base, and we used a convention where that service role we have appended the tenant ID to it. So now when you're aggregating the metrics, you could parse this message and get the tenant ID from that identity and also get that input tokens and put them together. And moving on to the agents, and again, let's assume multiple tenants are interacting with your service, and that the service would invoke an agent and assign a task to it, and the agent would interact with your large language model and completes the task for you. Before we dive into how to capture the metrics, we need to understand few things with respect to the agent. The way agent performs a task is whenever a task is assigned to the agent, it breaks down the task and then runs in 3 stages. That is pre-processing stage, orchestration stage, and post-processing stage. In each of these stages, it interacts with the large language model using a specific payload format, and then using a specific input payload format, it sends a specific payload format from the large language model. And if you look at those payloads, which I'll show you in a bit second here, you should be able to parse the number of input tokens and output tokens. So the idea here is the service role needs the service can the interactions the agent is making with the large language models. The way you would do that is, when the service is invoking the agent, it would enable the tracing. And once it enables the tracing, the agent will keep on sending back the tracing messages back to the service, with which you could parse into it and then get the number of input and output tokens. So let's say now the service can look into the tracing which is produced by the agent. For the pre-processing stage, you would see that the agent is using model input format in this format and then sending to a large language model. And the response you would is something like this, which is model invocation output. And if you look at those responses, you would see that it has the number of input and output tokens. I'm just showing you a format of these messages here. So if you look at the orchestration stage, you would see the similar kind of format. You would see there the model invocation output has the input and output tokens. If you look at the post-processing stage, again, you would see that it has a model invocation output message which has the input and output tokens. Now the idea here is the service can parse this model invocation output messages and get the number of input tokens and output tokens, and also from the service row, service can also get hold of the tenant context. From the tenant context, it can get the tenant ID and put them together and log that into the CloudWatch logs. Now let's look at the service code, understand how you could implement this. So in the service code first, what it is doing is basically invoking the agent. When it is invoking the agent, you could see that it is enabling the tracing. Since you have enabled the tracing, the agent would keep on sending you back the trace messages, and you could basically listen to the stream of messages and loop through those streams, and then using Metrics Manager, you basically parse those messages, the model invocation output message, and also from the input event, you would get the tenant context and put them together and log it to the CloudWatch logs. And now, moving on to the vector store. Here now, I'll specifically walk you through how you could capture some kind of a storage metrics for the basic tier where a collection is shared across multiple tenants. Let's assume you have the application plane. Within the application plane, we have a pooled collection which is shared across multiple tenants where you create index for each of your tenant. Before we understand how to capture the metrics, we need to take a step back and understand inherently how an open source serverless collection charges you for the usage. It charges you in 3 ways. One, storage cost, that is the amount of data stored underneath the collection. Indexing cost, the amount of computational units consumed when you're interacting with the particular index. And the search and query cost, that is the amount of computational unit consumed when you're searching and querying your data. So now, for each of these tenant indexes, you need to get the storage cost, indexing cost, and search and query cost. For the storage cost, if you look at these indexes, underneath these indexes, you will directly get the amount of data stored underneath these indexes. So pretty straightforward. But for the indexing and search and query cost, things become a little bit challenging and interesting, where you need to come up with an approach where you have to pick a metric which closely resembles that index and search and query cost. What I mean by that is, let's take an example of indexing cost. For the indexing cost, what you could pick a metric which closely resembles the indexing cost is again the amount of data stored underneath these indexes. So to put that all together, what I'm trying to say is for the storage cost and for the indexing cost, you could pretty much use the amount of data stored underneath the indexes as a metrics to derive the tenant cost. So the way you would do that is basically you could build a standalone service that basically hits your open source serverless collection and gets the amount of data stored underneath these indexes and tries to log that information into the CloudWatch logs. Again, here you could see that the challenge here is how do I get the tenant context? This service is a standalone service. It might not have access to the JWT token, and from that it might not be able to get the tenant context. Again, you could use a convention here. When you're defining your open source serverless collection, you could we could name the indexes with the tenant ID. So now this standalone service can hit your open source serverless collection and get the tenant ID from the index names and also get the amount of data stored underneath it, put them together and publish it to the CloudWatch logs. So now storage and index cost is done. The only left out thing is search and query cost. That comes into the picture when multiple tenants are interacting with your compute, and that compute would interact with your open source serverless collection through the knowledge base. Again here, for the search and query cost, you need to come up with a metric which closely resembles your search and query cost. One example would be you could capture the amount of execution time for a particular query. Use that as a metric for search and query cost. So let's assume you're using that, and then you would build a small library which basically captures that execution query and then passes that information, execution time of that particular query, and also the tenant context to the metrics manager, which kind of publishes this metrics. And again here, what I outlined here is more a fine-grained approach where I went into nitty-gritty details about how you could calculate or capture the metrics of storage cost of a particular tenant with respect to the open source serverless collection. But in reality, based upon your requirements, you could adapt a more coarse-grained approach where you could use some kind of an approximation where you pick one metrics and use that metrics as an approximation and slice and dice your cost across your tenants. Like in this case, you could pretty much use the amount of data stored underneath these indexes and use that metrics to slice and dice your cost across your tenants. So at this stage, in your architecture, you have all the metrics captured in your CloudWatch logs with the tenant context. So what you need to do is aggregate the metrics. I'll try to paint a high-level picture here about how you need to aggregate the metrics, and then we'll deep down, we'll double-click onto those components and we'll understand in a bit more detail. So the first thing what you could do is build some kind of lambda function, which basically uses a CloudWatch insights query to interact with your CloudWatch logs and get the tenant, aggregate the percentage of consumption across your tenants. Basically aggregate all the number of input tokens and output tokens generated for each of your tenants and get the percentage of consumption across your tenants. Once you get that, then you could use some kind of you could use Athena service and interact with the cost and usage reports to get the total service cost. And then you would multiply the percentage of consumption with the total service cost to derive the cost per tenant. You would store that information in some kind of a DynamoDB table. And once you have that information, then you could visualize that data and slice and dice the data whichever way you would anticipate. And then now let's look at the code of this lambda function, the lambda aggregated function, and try to understand how to implement this logic. So the first thing what I said is you need to query the metrics. The thing what you could do is you could see in this code it is using the CloudWatch Insights query to get the number of input tokens and output tokens with the tenant context, basically the tenant ID, across your CloudWatch logs. The next query, basically, it is trying to get the total tenant input and output tokens across all the tenants. And then you're kind of like dividing both of these values to get the percentage of consumption across your tenants. So basically, you're trying to get the tenant attribute percentage for input tokens and output tokens. The next thing you need to do is basically get the service cost. For the service cost, again, as I mentioned earlier, we said you could use Athena to interact with the cost and usage report to get the service cost. In this case, you could execute a Athena query, and then once you execute this Athena query, and from the results, what you could do is parse and get the service cost for the input tokens and output tokens for using a particular LLM model. So now you got the service cost, and you also got the percentage of consumption. The next, what you need to do is basically calculate cost per tenant. For that, what you need to do is, as I mentioned earlier, you just have to multiply both of them. That's what this method is doing. This method is basically multiplying the tenant percentage against the total service to get the input tokens and output tokens, how much it is costed for the input tokens and output tokens for each of your tenants. And then you're kind of like combining those to get the total cost for this service, in this case, basically the bedrock. And once you have that total service cost, you would store that in some kind of a DynamoDB table. This is how you could calculate cost per tenant for your architecture. And moving on to the last architecture challenge, which we'll talk about today, is noisy neighbor. One way to mitigate the noisy neighbor conditions is to enable some kind of a throttling experience at your, for your tenants at API level. In here, I'll try to showcase you how you could implement that throttling experience using tenant token usage. If you look at the basic tier and the premium tier, there is some piece of an architecture which is common, which is nothing but this. So basically, you have an API gateway. At the API gateway, you use Lambda authorizer to authorize the request and pass that request back to the microservice, and the microservice would interact with the bedrock. And now, what you could do is, you might be already familiar that at the API gateway level, you could enable some kind of a usage plan which kind of like throttles the request. Additional to that, what you could do is you could introduce some kind of a tenant token usage plans. And again, I'm just giving you a hypothetical number here, but you could have a different usage plan for basic tier and different for premium tier. And now when you're onboarding a tenant, you would assign this token usage plan, and that information again would be captured by your tenant management service, which will reside in your control plane. And now, what you need is a piece of an architecture which in real time needs to aggregate the number of input tokens and output tokens generated for each of your tenant. The assumption here is that obviously your architecture is already capturing those metrics. And for that, what you could do is build this simple architecture. That is, again, you could use some kind of Lambda function which queries your CloudWatch logs and tries to aggregate those number of input tokens and output tokens across your tenants and publish and push that into some kind of a DynamoDB table. And again, based upon how real-time you want this information, you could build more robust architecture to get this real-time consumption of, or the generation of tokens. And once you have that, when the request comes to the API gateway, the Lambda authorizer would invoke, and the Lambda authorizer, using the tenant context or the tenant ID, it can reach out to the control plane. From the control plane, it can get the usage plan assigned to that particular tenant, and then in real time, it can hit this tenant usage table and get the current usage of that particular tenant and compare both of those values to decide whether to allow or disallow this particular request. And again, at the API gateway level, you could enable the caching. If you enable the caching, this logic might not run for each and every request, but again, based upon your requirements, you can change those configurations which suits your requirements. Now let's double click and look into the code of this tenant usage calculator and also the Lambda authorizer to understand this in a bit more detail. So for the tenant token usage calculator, the first thing it does is basically it uses CloudWatch log queries and tries to aggregate the tenant usage by tenant, and then stores that information in some kind of a DynamoDB table. And then for the Lambda authorizer, you would make, using the tenant ID, you make a call to the control plane to get that assigned token usage for this particular tenant. And then you invoke a method to check the limits. And if you look at that method, the first thing it is doing is basically it is hitting that tenant token usage table to get the current token usage for that particular tenant. And then basically you're comparing the assigned tokens to that particular tenant against the token usage to decide whether to allow or disallow this particular request. And then finally, just to summarize some of the takeaways for this session, We have introduced a couple architectures through basic tier and premium tier, but again, be aware that there are AWS service quotas and limits to it, and try to look at those things and build your own architecture based on those service quotas. As we are outlining here, when you're building this architecture and going through this architecture, we try to resolve each and every SaaS architecture challenges so that it will yield you a robust architecture. So try to think about in those angles when you're building your own architecture. Try to resolve various SaaS architecture challenges which are specific to your requirements that will yield you a robust architecture. And then when you're building a SaaS solution, you would obviously try to shoot for providing a tenant-based experiences. For that, try to leverage a tiering strategy. As we outlined, we try to define a basic tier and a premium tier. Through that, we are trying to provide a different experience for your different tenants. And then when you're implementing tenant isolation and data partitioning, the way you would implement, the concepts would be similar, but the way you implement them might be different. Like for example, in this case, we used OpenStack serverless collection. We walked you through how you could implement tenant isolation. But again, in reality, you might use a different vector store. You might have a different tool to implement it. But the idea is the concepts are the same, but the way you implement might be different. So just keep that back in your mind. And then utilize IAM wherever possible to implement tenant isolation. And then when you're capturing the metrics, always try to capture the metrics with the tenant context so that you could aggregate the metrics later on across your tenants. And again, once you have that information, you could use that in different ways. Like for example, you could see in our session, we captured the metrics, the number of input tokens and output tokens generated for each of your tenants with the tenant context, and used that to derive cost per tenant, and also use the same metrics to enable some kind of a tenant throttling experience based upon tenant token usage at the API gateway level. And this is the GitHub repo link, which we mentioned earlier, where you have most of this code. And this is the new workshop which we built. And we are running this workshop on Wednesday morning. The idea of this workshop is a SAS405. If you're interested, feel free to join that workshop. I'll just pause for a minute. Yeah. And then these are some of the additional sessions which are presented by my teammates. If something piques your interest, feel free to join these sessions. And these are some of the workshops and builder sessions. And finally, thank you. Thanks for stopping by and being patient and listening to our talk here. And I really appreciate you guys being here. And then please do fill out the survey.